So, hello everybody. Today we're going to learn a bit about how momentum is stored in electromagnetic fields. We're going to derive everything starting from the Lorentz force law, wherein a charged particle in an electromagnetic field feels the force that I've written in the screen. So we're going to begin from this and build up our theoretical foundations all the way to Maxwell's stress tensor, and we're going to look at the most common interpretation of the electromagnetic momentum continuity equation. So we're going to begin from the electromagnetic Lorentz law, wherein a charged particle Q in an electromagnetic field feels a force that's going to be given by the charge magnitude, its velocity crossed with the B field, the local B field it experiences, plus the local electric field, right? So the electric force and the magnetic force. That's what we're going to begin from. That's the Lorentz force law. So provided an arbitrary field, right? So you've got some configuration of field. So you've got X, Y, and Z, and you've got a certain field in space that's defined, right? So at every point you've got E and B defined, right? And obviously they're going to follow Maxwell's equations. We're going to write them down shortly. So we'll see in this video that these fields in and of themselves carry momentum, right? These fields in and of themselves carry momentum, and we're going to see that by trying to write this Lorentz force law completely in terms of the local fields instead of Q and V and everything. We're going to trying to write everything in terms of E and B, and we'll see how that is shortly. So let's talk a bit about what F represents right now, right? So F represents the total rate at which the mechanical momentum changes. The total time derivative of the mechanical momentum, right, of a single particle, and we're going to generalize that shortly. So let's try to do that, right? So this is for a single particle, and if we're talking about the local force density, that is, if we're talking about the force that is felt per unit volume, per unit small volume of that field, then we're obviously going to have to use the local charge density instead of the local charge magnitude, right? With that, we're going to switch the notation to small f. We're going to use small f to represent small f prime to represent the local force density, right? Force felt per unit volume of that field at a position R, right? At a position R. And that's going to be given by rho V cross B plus E. And okay, we're going to distribute rho inside. So rho V crossed with B plus rho times E. And we know what rho times the velocity of that local charge density is. That's just the volume current density crossed with B plus rho times E. Okay, and now we're going to use Maxwell's laws in order to write J and P completely in terms of E, so that at any position vector R in the electromagnetic field, we're going to obtain the local force density completely in terms of just E and B, right? We want everything just in terms of E and B. So we're going to write the relevant Maxwell's laws, right? Let's write what they are. Okay, so we're going to use two Maxwell's laws, right? We're going to use two Maxwell's laws. Let's see what they are. The first one is for J, for which we're going to use the corrected Ampere's law. The curl of the B field is mu naught times J plus mu naught epsilon naught times the time derivative of the electric field. And the second one is going to be for the local charge density, wherein we know that the divergence of the E field is rho over epsilon naught. So with those corrections, With those corrections, our equation for the local force density becomes something like rho cross B crossed with B over mu naught. And I think you follow the algebra. It's not that hard. The time derivative of the electric field crossed with B plus epsilon naught times the divergence of E field times E. All right. So that gives the expression for the local force density. And that's about it, actually. But this can be written in more illuminating, in a more illuminating fashion, as we'll see. So consider this term. Consider this term. Let's try to see how we can simplify this. So what we're going to use here, right? What we're going to use here is this is an expansion of the time derivative of this particular cross product, right? We know that this is going to be dE over dt crossed with B minus dB over dt crossed with E, right? So let's try to use this in the equation that we had, right? So then our expression for the local force density becomes something like negative B cross the curl of B over mu naught minus epsilon naught. And okay, so we're gonna use this the expression that we obtain for this particular term there, which is going to give us epsilon naught mu naught times actually, let's try to simplify this equation a bit more, right? Let's try to simplify that a bit more. So let's write this equation explicitly in terms of dE over dt, actually, right? So dE over dt crossed with B, which we want there, by the way, that from this equation is going to be, so this particular thing, I think you can relate with the pointing vector, right? This particular thing is related with the pointing vector. In fact, I'll write what the pointing vector is, right? For revision purposes, it's going to be given by the cross product of E and B divided by the permeability of free space, right? So this particular thing, that's going to be mu naught times the time derivative of the pointing vector. And if this term goes to the other side, that's going to give us negative E crossed with dB over dt, right? I'm sure you realize the property of the cross product that I've used. Okay, so I'm going to use this particular thing there, which I've obtained, using elementary principles of vector calculus, right? This particular product rule. And I'm going to use that for dE over dt crossed with B. Okay, so let's see what that gives me. All right, the first term is going to be the one with a pointing vector, of course. The second term is going to be, all right, so this can be written in actually a more illuminating way, right? ds over dt minus, Faraday's law tells us that the negative time derivative of the magnetic field is the curl of the electric field, right? So we're going to obtain something like E crossed with the curl of E. All right. So we've got this term. We've got the second term, right? We've got the second term replacing dE over the time derivative of E crossed with B. We've got the second term. We're trying to replace that. We've got this term, and we've got the other term as well. That's epsilon naught times E cross the curl of E plus, and we write the final term, E. Okay, the epsilon naught times the divergence of E times E. All right, so I think we have the full picture. So what we did was we wrote that term, we wrote the final term, and we basically replaced this thing with something that allowed us to write things in terms of the pointing vector, right? We used this particular product rule. All right. So our equation for force density probably has now it's not yet written in a completely illuminating manner, but then it has made some progress, right? And we can make more progress actually, and we'll see that shortly. All right. So let's think about these two terms. I think they've got something in common. They're both one field, of which we've taken the cross product with the curl of that same field, right? This is B cross the curl of B, and this is E cross the curl of E. I think that should tell us a bit about what product rule we're going to use next, right? So the product rule that we're going to use next is this particular product rule, which is related to the gradient of a dot product. The gradient of a dot product. So let's say we've got two arbitrary vector fields, right? This does not represent the magnetic field. This does not represent the vector potential. These are arbitrary vector fields, right? Gradient of a dot is going to be given by A cross the curl of B plus B cross the curl of A. So this is one of the hardest product rules that I find quite hard to remember, but then it's not that hard even to remember once you get the grip around it. Next thing being delta dot A times B plus delta dot B times A. All right. So this is the whole product rule that's written for two arbitrary vector fields A and B. So we're going to do this for A is E, the electric field, and B is E, the electric field again. All right, so let's see what this yields. Okay, so this yields two similar terms because A cross the curl of B and B cross the curl of A are going to be the same for A and B both being the electric field. So that's going to give us 2 times the curl of the electric field, 2 times E cross the curl of electric field, and that term, by the way, is what we want for our force density to simplify potentially, right? Let's see. Plus, and these two expressions give the same thing, and that's going to be delta dot E times, I'm sorry, I think I've written the product rule with a bit of error. So this product rule is actually B dot delta times A plus A dot delta times B, right? Mistakes happen. All right. So then both of these are still equivalent if B and A are both E, right? So E dot delta times E and multiplied by 2, right? So that is our product rule that we're looking for. And for E dot E, that's basically the gradient of the E squared scalar field, right? We can take the 2 to the other side. We can take the 2 to the other side of the equation, right? And then we can write this for what we want, which is the cross of E with the curl of E, which gives the gradient of E squared over 2 scalar minus E dot the del operator whole times E, right? So this is what we want to replace in our force density equation. This is what we want to replace in our force density equation. Let's write that. Okay, so let's put that towards the right side. And a similar law can also be written for the B field, actually. So B cross the curl of B is going to be the gradient of the B squared over 2 scalar field subtracted with B dot the del operator whole times B. All right, so these are two things that we're going to use, right? E cross the curl of E with the third term and B cross the curl of B with the first term. Let's see what that yields. All right, let's see what that yields. So that yields something like okay, that yields something like 1 over mu naught negative the Laplacian of B squared over 2 field plus B dot the del operator B. I hope you can see that this came from that term, right? When we're replacing this there, that's going to be for the B. Epsilon naught, we're going to repeat the same story for E. Okay, so gradient of E squared over 2 scalar field plus E dot the del operator times E, right? So that's it for B and E. So I've replaced these two things. If you can see that. I've replaced these two things. And I'm going to write this term after that, right? It does not matter what the order of addition is because we're just adding the terms. And I'm going to write this particular term with the pointing vector at the end. And I think the reason for that will be clear pretty soon. Okay. So I think we're about to end it with one final touch to rearrange the terms. Let's write all the E's pretty clearly and let's write all the B's pretty clearly, and I think a nice little symmetry will be apparent once we're finished with that. Okay, so this whole thing can be written pretty neatly, right? This whole thing can be written like this. All right, so we're gonna get E dot delta plus delta dot E. All right. So I was about to factor E out of that, but I decided to skip that idea. Okay, all right, so this is for the E term. I hope you can see where these terms come from exactly, right? So this term, and this term, I basically collected those terms. And for the B, it's basically this factor of permittivity replaced by 1 over permeability, and it's basically the same thing, right? B dot delta B plus delta dot B minus the gradient of B squared over 2 scalar term, right? This whole thing subtracted with the pointing vector term, which involves I think we can write the permeability times the permittivity as 1 over c squared, c being the speed of light, right? So I think you'll notice a certain discrepancy, which is that I wrote this term, I gave birth to this term from thin air, right? This term appeared from thin air, but I think you can also see why. It's because it does not matter even if I include that term, because the divergence of B is just 0, right? You can add something with 0 without changing what that thing is, right? So I think the reason why I added that term is also clear, also pretty clear. It's in order to maintain a nice little symmetry between E and B, right? So there's this E dot del times E term for E. There's the analogous B dot del times B term for B. As the del dot E term times del dot E times E term, as the del dot B times B term. There's the gradient of E squared over 2 scalar field, and there's the gradient of B squared over 2 scalar field. And there's a nice little pointing vector with both of them crossed, divided by the square of the speed of light, right? So it's all nice and symmetric right now. And this actually ends the story for our quest of writing the local force density completely in terms of E and B. Actually, this should be our final answer, and I know that this might not satisfy a lot of you out there because this is too messy, right? This is too messy. So let's try to interpret this in whatever possible way, right? Let's see what we did. Okay, we began from the Lorentz force law, right, written for particles, and then we generalized something to something that we called force density, right? So this was basically the force felt by the particles, right? Because particles are distributions, they're not discrete particles. We assume that particles are distributions. Actually, they're discrete, but for small enough charges spread out, for uniform distributions, and for a certain distribution function to work out, for the calculus to work out, we need to assume a distribution, right? So in order to deal with distributions, we defined a certain force density per unit volume, right? So this was the force felt by the particles per unit volume existing in that electromagnetic field. And since the particles, the currents, the local currents, and the charge densities, they're in it of itself related with the fields, right? Related with the local fields. The current density is related to the curl of the B field, the local curl of the B field, and the local time derivative of the E field. The rho itself, that is the local charge density, is related with what the divergence of the E field is at that point, right? The charges and currents themselves in space where there is an E field present, they're related with the E and B fields themselves. That means that the total mechanical force that's felt by the particles per unit volume, that is the local force density, can be written completely in terms of what the E and B fields are there, right? So, all right, let me summarize. This means that in space, right, there's a certain B field and E field present, right? So we can take a certain volume element, at a position vector r, right? Then I can tell what the force density F is, that is the mechanical force that's felt by the particles and currents, by the charges and currents that are situated in this small volume d tau dash that's situated at r, right? I can tell what that is. I can tell what the local force density is purely with the knowledge of the E fields and their variation within this volume, right? So there are some E dot del terms, there are some divergence terms, there are some gradient terms, but purely if I know what the B field and E field are around this region, I know what the local force density is, right? And that's the beauty of Maxwell's equations. The only problem that we have with this particular expression for the force density is that this is ugly, right? For one thing, this has 7 terms, right? A force law or any reasonable physical law shouldn't have 7 terms. So something that comes to our rescue is a very special object that we define, which is a tensor quantity, right? Okay, so let's develop a separate story from here on onwards, right? Let's call this equation 1, let's call this equation I, right? And let's develop a completely separate story. All right. So after having, digested everything that we've done thus far, so we're going to develop a completely separate story. One story is that the force density, the local force density, can be written completely in terms of the fields, and that yields a pretty ugly expression, right? Though the expression does seem to have some symmetry between E and B, it yields a completely ugly expression. The second story that we're going to look at is Maxwell's stress tensor. All right, and this thing is going to help us simplify, very brief spoilers. This thing, Maxwell's stress tensor, is going to help us simplify all of this. It's going to help us simplify all of these terms, apart from the pointing vector term that we wrote at the end. All right, so those were our spoilers. Let's see what this is. All right. So this is a tensor quantity, all right? The notation is that we write a t and a double arrow above it, or we can write it as Tij, and I'll tell you what this is. All right, I'm going to write a certain equation, and I'm going to tell you what this is. All right, so Tij is defined as epsilon naught times Ei times Ej minus delta Ij E squared over 2 plus the same thing for the magnetic field. Bj minus delta Ij b squared over 2. All right. So think of this as a tensor quantity with 9 elements, right? Think of this as a tensor quantity with 9 elements. So like T is a tensor quantity with 9 elements. So the elements are Txx, Txy, Txz, right? So X represents the row of the tensor, right? X represents the row of that tensor. A particular X represents the row of that tensor. Tyx, Tyy, Tyz. tzx, tzy, tzz. So think of this t as a tensor object, right? Inside of which we're going to encode all of this. And we'll see how very shortly, right? So we're building it as a separate story, right? We're learning the notational tricks and the notational stuff and the definitions of what this is and how this can, condense all of these 6 terms into just one term. Right, we're basically developing a sophisticated object that allows us to condense all of this, allows us to include all of this in just one term, right? And we're going to add a physical meaning to this tensor quantity as well. We'll do that shortly. All right, think of T as really an object with 9 elements. All right, so let's talk a bit about the definition of each element, right? So each element is actually defined for I and j. And I and j, by the way, I can be x or y or z. In fact, let me capitalize everything, right? I can be either the x component, the y component, the z component. J can also be either the x, y, or z component. So for example, let's take one particular term. Let's take a diagonal term, and then we're going to take an off-diagonal term, right? And one diagonal term and one off-diagonal term should tell you the complete story of, how and why things are defined. So let's take tyy and tyx, right? All right, let's see what tyy is according to the definition that we've written there, right? So that is epsilon naught times ei times ej. And since I and j we've both taken to be y, right? We've taken the tyy element. That gives us ey squared, right? Ey squared. So this is the yy element of the T object, right? Think of it like that, the tensor object. So ey squared, that's what the first term gives, minus, and I'm yet to talk about what this delta means. So this actually, delta is the Kronecker delta operator. All right, let me talk about what that is. So delta ij, we call this the Kronecker delta operator. Delta operator. And this really just is a way to say that if I and j are the same, then delta ij is 1, right? So include this term if I and j are the same, if I equals j, and do not include this term, that is, let the Kronecker delta operator be 0, right, if I is not equal to j. So it's just that simple. So for example, if we're taking delta yx, that is I as y and j as x, then this term is 0. But if we're taking del zz, that is for the same I and j, then this should really be 1, right? So it's basically saying only include this term if I and j are the same, if you're taking diagonal terms, right? So we'll see why, this weird definition, why we've defined this such a weird object with, different definitions for diagonal and off-diagonal terms and everything. But, okay, we're going to have a bit of patience, right? So let's, explore a bit about what this object is, what its terms are, right? Okay, so we were writing the tyy element. We'd finished with the first term. Going on to the second term. Now, since we're writing it for tyy, that is I and j, they're the same. That means that we include that term. E squared over 2 plus 1 over mu naught times this gives by squared. It's the same thing for b, right? The definition for b is just symmetric. So that gives you the tyy element. There's a more illuminating way in which you can write this. Ey squared minus ex squared minus ez squared over 2. I think you see what I've done there, right? I've written the magnitude of the E field in terms of its components, basically. And I get by squared minus bx squared minus bz squared over 2. So that really gives me the tyy element, all right? And let's also talk about the tyx element. right? That, according to my definition, is going to be epsilon naught times, I think you can see the first term, it's just EI times EZ. So that gives me EY times EX. And since the Kronecker delta operator is it's just 0 for non-symmetric I and J, this is all that the electric field terms are, right? And it's the same thing for the magnetic field as well, right? BY, BX. And I think you can also see there's a symmetric relationship between TYX and TXY, because nothing would really change if, I evaluate TXY instead of TYX, right? The terms would just switch and the product of two things is commutative. So, it's going to yield me the same result. So TYX is just TXY. So the matrix is symmetric, right? Symmetric about the diagonal. It's the diagonal terms that are a headache, but the off-diagonal terms don't, I don't think they have much story to tell. But then still, so we've got a tensor object with 9 elements, right? We've got XX, XY, XZ, and, all of that for Y and Z as well. So we've got 9 elements, and we've written 2 of the elements to exemplify how these elements are defined. So this is how a general term for that matrix, for that tensor is defined, where I and J can be components. And this applies for 9 elements, all 9 elements of the tensor quantity, right? Which we call the Maxwell stress tensor. Let's explore what it means to take a dot product with this tensor quantity, with the Maxwell's stress tensor, right? So we're just, exploring a bit of mathematics and exploring a bit of hows and whys and in the notation. All right, with the Maxwell's stress tensor. So we're gonna see what it means to take the dot product of a vector, right? Of a vector which has x, y, and z components with the Maxwell stress tensor, and that tensor, let me write that again, it's symbolized by a double arrow above t, and it has txx, txy, txz, tyx, tyy, tyy, yy, tyz, tzx, tzy, tzz elements. So what exactly does it mean to take a dot product with a tensor quantity, specifically the Maxwell's stress tensor quantity? All right. So how things have been defined is that when you're taking this dot product, that is A written to the left and the stress tensor written to the right, right? This dot product, let me actually, write that in a column form so that, things are more illuminating. We're taking the dot product, this with the whole thing, with the whole stress tensor, TYY. All right, so what exactly does it mean to take the dot product with a vector and the Maxwell stress tensor? Or just the tensor? All right, so turns out, so there are 2 ways to write this in notation, right? We can either write the vector to the left and the tensor to the right, or we can write the tensor to the left and the vector to the right, and these are not the same thing. These are not the same thing. For a tensor, the order of notation matters, right? It matters where relative to the tensor quantity you write the vector before taking the dot product, right? So because it's only relevant for us in our discussion that the vector is written to the left, I'm going to talk about what it means to write the vector to the left and then take the dot product. So one of the things that we need to understand is that this dot product, A dot producted with the tensor quantity is not a scalar quantity, right? It's not a scalar quantity. It's a vector. It's a vector quantity. All right. So this is one of the things that's different from a regular vector to vector dot product, right? A vector to a tensor dot product is actually going to yield a vector, another vector. And we'll see how that is defined in a while, but we need to digest this in order to go further with our notation, right? So that's the thing I wanted to tell about dot product with the Maxwell stress tensor. It means that a vector dot producted with the Maxwell stress tensor does not yield a scalar quantity but a vector quantity. And how is this vector defined? Well, let me talk about how one particular component of this is defined. All right. A dot t in and of itself is a vector quantity. So let's see how the x component is defined for the dot product, right? So the x component is going to be something. We're going to write that right there, right? Let's give a bit of space because, you know, the definition is quite large. I don't want to spoil things for you. Let's see that as we go. It's going to have a certain y component and it's going to have a certain z component. For the x component, if and only if the vector is written towards the left and the tensor is written towards the right, that's the conventional thing that we use, notation matters. If the notation is such that the vector is written towards the left of the dot and the tensor towards the right, then what it means to take that dot product is that its x component is given by the dot product between these two vectors, this and this, right? So we're going to take the dot product between these two. And let's see what that is. That basically means that we take the product of the first two, the product of the second two, and the product of the third two, and we basically add them together. It's like the dot product of a regular set of two vectors, right? So ax times txx plus ay times tyx plus az times zx. So that's what it means to take the dot product, the x component of this dot product, right? The y component of this dot product is again defined similarly. You take the dot product between this and the y terms, right, in the column, right? So this is how you map. Anyway, if we proceed, that's going to be ax times txy plus ay times tyy plus az times tzz. And following similarly, the z component of the dot product is going to be ax times txz plus ay times tyz plus az times tzz. All right. So if we're going to write this more precisely, right, the ith component, or let's call it the jth component of this dot product, is going to be given by the sum ai times tij, where I goes from x and then y and then z. And I think you know what this thing is, right? J remains fixed for a particular component, right? So J remains fixed for a particular component. If J is z for that particular component, then you're taking the z component, then the second index for the corresponding tensor element remains the same. Z is going to be that index for the third term, right? For the third component. Y is going to be that index. I'm sorry, there's been a certain mistake there. It's supposed to be zy. For the y element, right? we're going to fix the second index at y. And for the x, we're going to fix the index at x, right? So more formally written, the jth component of the dot product, when the vector is written towards the left of the dot, by the notational convention. The notational convention is that when the vector is written towards the left of the dot, right, we take this particular sum, which is the same thing as, taking the dot product between two regular column vectors. So for the x element, as I said, we take the dot product between the vector and the x terms. The x terms basically meaning that the x is the second index, right? Or the x column, yeah, or said more precisely. All right. So that's about it for how the dot product is defined. And let's move on towards what it means to take the divergence now, right? The divergence is basically the dot product with the del operator, right? That's one of the foundational things in vector calculus that we learn. So what does it mean to take the divergence? Okay, so we've learned about what it means to take the dot product of a vector with the Maxwell stress tensor. And now we're moving on to what it means to take its divergence. All right. And divergence, you need not worry, is defined very similarly. It's defined very similarly. All right. So we're going to continue our story from equation 1 after this particular section when we learn what the divergence is. And everything's going to make sense at the end. All right. So the divergence of this Maxwell stress tensor, right? This divergence is basically going to be, the dot product between the del operator, right? This is the del operator. I hope you know what the del operator is. So d over dx and d over dy and d over dz. This is the del operator, right? It's the same thing as the ax written as d over dx and ay written as d over dy and az written as d over dz. So this is the del operator, and we're going to take the dot product with the tensor. So the tensor is txx, the first element, txy. I'm just going to fill this in without bragging too much. All right, so we're going to take this particular dot product. Okay, so so remember our initial definition of the stress tensor, where we said that the stress tensor, the ij element, was defined. So I'm going to write this particular definition for what the Maxwell stress tensor was again, right? This is Maxwell stress tensor for E and B fields in space. Let's write that again, and let's try to take this dot product this time. Let's try to take this dot product. All right. So Tij is going to be given by the same thing that we wrote for it a while back. Ei times Ej minus the Kronecker delta, E squared over 2, plus 1 over mu naught times Bi times Bj minus the Kronecker delta, B squared over 2. So that's the definition of the Ij element, right? So, okay. We're going to see what one of the terms is, because, applying the definition for all 9 elements of the stress tensor, it's just going to be too much work. So let's just see what the z component of this dot product is, right? So what is the z component of the divergence? And again, one thing I have to tell about the divergence is, the divergence is basically the same thing as the dot product, the del operator with the tensor matrix, right? So because the dot product was a vector quantity, the dot product is not a scalar quantity. It's a vector quantity with 3 components, right? We had 3 components when we took the dot product of any arbitrary vector A with the stress tensor. That means the divergence is also a vector quantity. right? This divergence is a vector quantity. Let me write that explicitly. The divergence is not scalar, right? But a vector. It's a vector quantity. And what would the zth element be when the divergence is written towards the left side? By the same notational convention that I talked about a while back. So this is going to be, the zth element is going to be this del operator dot producted with the zth column. Okay, so what is that going to be? That's going to be d over dx times txz plus d over dy times tyz plus d over dz tzz. Okay, so I promised to draw a connection between the second story, which was about the Maxwell stress tensor, right, which we defined to be a matrix of this general definition. I promised to connect the story of Maxwell's stress tensor with the story of the local force density, and all of this will make sense in a while. After we, you know, evaluate what this is. Okay. So, okay, let's write what these are first of all, right? Let's write what xz and tyz and tzz are. So txz, it's not that complicated. We already know what txz is. Txg is just going to be epsilon naught over 2 exez plus 1 over 2 mu naught bx bz, right? And also I think we already noticed the symmetry between E and B in the definition for the tensor. So whatever it is for E, it's just 1 over instead of epsilon naught, we use the reciprocal inverse of the permeability, and it's just the same thing for B. So let's try to do whatever the thing is for E, and then it's just going to be the same thing for B, right? So we're gonna omit the B terms once we delve into the partial derivative calculations in a while. We're going to omit the B terms, right? We're going to evaluate the E terms, and by symmetry we're going to write this, whatever we obtain for the E terms, we're going to compare with the B and write for the B, and we know what that is going to be. It does not require too much sense, and it only requires a certain bit of intuition to do that, right? So txz, we know what txz is by the previous definition. We know what tyz is, right? Tyz, we know what that is. I'm sorry, the factors of 2 are not present for non-symmetrical I and z. Anyway, tyz is ey times ez plus 1 over mu naught times by times bz. And tzz, okay, this one might have a certain length. This one has a factor of 1 over 2 ez squared minus ey minus ex squared plus 1 over 2 mu naught b z squared minus bx squared minus by squared, right? So these are our things for tx and ty and tz, and we're now going to take the partial derivatives in order to evaluate the zth component, one of the components for the stress tensor. Okay, when we evaluate this, I think the story is going to be pretty clear as to what direction I'm going to lead this discussion to next. Okay, so let's evaluate this. The zth component of the tensor, the divergence, the z component of the divergence, spoken more precisely, is going to be... All right, and now I said that I'd only write the electric field terms, and the magnetic field terms would be the same as what we obtained for the electric field terms. So let's just write things for the electric field terms, right? Ez plus d of dz epsilon naught over 2 ez squared minus ey squared minus ex squared, right? And the magnetic field terms are going to follow, right? B field terms. These are the B field terms. Those are going to follow. Anyway, let's try to move forward and evaluate what the E field terms are. So the result that I'm going to obtain is epsilon naught, factored out of all E field terms, because there's epsilon naught in all three terms, right? We can see that pretty clearly. We factor out the permittivity and, use a mixture of chain rule and product rule for the first term, dEx over dx times Ez plus dEz over dx times Ex plus all right, we're not gonna have to use these brackets. All right, also we need a bit of space, plus dEy over dy Ez plus dEz over dy ey plus. All right, I'm going to evaluate these directly, having applied the chain rule. I think you're going to go through the algebra and think about if the cancellations work out right. All right. So this the first term is going to be Ez times dEz over dz. Second term is going to be Ey dEy over dz. Third term is going to be Ex dEx over dz. All right. So I've evaluated all of the things. For right now, it looks very messy. It looks like it's just mess, right? There's nothing very illuminating about this. But wait for the next two steps of manipulating this equation, and everything's going to be clear with how this story about Maxwell's stress tensor and its notation and taking the divergence is going to be connected with the story of the local force density. All right, so let's try to collect the divergence terms, or let's try to collect the terms with Ez in them, right? So I've got three terms thus far, and let me underline them by yellow actually, right? So I've got three terms with Ez in them. Let's try to factor that out because we're evaluating the Z term. Let's see if this yields a nice symmetric expression, that we can write in terms of divergences, or maybe E dot del operators, or something, right? Let's try to see if we can find anything of that sort. All right. So let's see. So yeah, we did find three terms out of which we could factor out Ez, and the remaining just becomes the divergence of Z. If you're a bit clever with these terms, right? We can write this as dEx over dx plus dEy over dy plus dEz over dz times Ez, right? And this is just the divergence in Cartesian coordinates, if you remember what we derived long back, right? What the divergence was in Cartesian coordinates. Let's see if we also have something like an E dot del, right? Which would basically be Ex times del operator in x times Ey, a partial derivative in y, plus Ez, a partial derivative in z, and maybe Ez because we're taking the z component. And we actually find two of the terms, right? One of the terms is right here, right? It's just this Ex times the partial derivative of z, and the other is just this, right? It's just Ey times the partial derivative of z with y, and this term is actually missing. So let's try to add that term. Let's try to add that term, and let's try to subtract that term. So I'm actually gonna underline them with a separate color actually, right? So that we don't mix things up. So these are the yellow terms with which I could factor Ez out of, and the remaining would be the divergence. And for E dot del terms, right, I have selected two of the terms already. I've found two of the terms already. One of the terms that I've not yet found, right, one of the terms that I've not yet found is this term, the third term. And let's do my part by myself in adding that third part. So When we add that, it's just going to be dEz over dz times Ez, and we're going to have to subtract that as well, right, in order to stay consistent with the information that the equation is giving us, right? And with that, the E dot del term also becomes completed, right? If we factor out Ez out of all of the green terms, right, out of all of the green terms, if we factor out Ez, what's remaining is this Ex times d over dx plus Ey times d over dy plus Ez times d over dz whole times Ez, right? And this is basically the zth component, because we're evaluating the zth term, right? And there should be symmetry for x and y terms as well. We should get something very similar for the x term, right? For the x term of the divergence, right? It's just a simple replacement. We replace this Ez with Ex for the x term, this Ez with Ex for the x term, right? And it's about completed. It's about completed, but we have three remaining terms exactly. I'm going to underline them by blue. We have three remaining terms exactly, and let's make some space for them. Right? Let's shrink the other 6 terms down. Let's make some space for the remaining 3 terms, and that's just Ex times Dex over dz plus Ey dEy over dz plus Ez dEz over dz, right? So this just looks like, somebody's taken the partial derivative of this whole thing, that is the squared of the electric field, right? Somebody's taken the partial derivative of this, right? This is what this term looks like. And halving that, right? So what is this? This is basically half of the z term of the gradient, half of the z term of the gradient of E squared, right? And I think this rings a bell. This rings a bell. If it doesn't yet ring a bell, it will ring a bell very soon, right? This whole thing for the E terms, and we've neglected the B terms, by the way. I don't know if neglected is the right term. We've omitted them, in order to catch up with them at the end, because whatever we get for E, we're going to get the same for B, right? We found what the third term was. Somebody basically took the gradient of E squared scalar field and took their z component. All right, so we're going to rewrite the step in a very neat format, right? So this is the divergence of E in Cartesian coordinates, and we use the divergence operator, times Ez, right? Plus, this is basically E dot del operator and Ez, and this is, somebody basically just took the z component of the gradient of the E squared scalar field. Somebody just took the z component. So that's what we get for the E field z components of the divergence. And for the B field, obviously, we're going to get something very symmetrical. Right? Let's still omit the B fields right now. The B field terms are there, right? You know how to recreate the B field terms from looking at this. But this is still not quite what I'm aiming at. All right. So consider what I evaluated here. I basically evaluated the z component of the divergence of the stress tensor. I evaluated the z component of it. So what if I write the whole vector? What is this going to look like, right? So I think it's pretty apparent, right? If we were evaluating the y component, this would almost certainly be Ey, right, pointing towards the y direction. This would be Ey, this is in place of Ez, and instead of taking the z component of this gradient of the E squared scalar field, we'd take this y component. So I think this yields a very nice symmetrical thing for what the divergence of the stress tensor is. It's del dot E, which is the divergence of E, times E, right? If we're to generalize for the whole vector, plus E dot del times E again, right? Note that these are not the same things. Minus half of the entire gradient of E squared, right? Taken with Z component for the Z component of the divergence, taken with Y component for the Y component of the divergence, and everything, right? And if we're going to complement this with the magnetic field terms that we omitted for simplicity in calculations, notice what we're going to get. Del dot B for B plus B dot del for B at half of the gradient of B squared, scalar field. And if we're going to write that in a bit more illuminating form, it's going to be del dot E plus E dot del times E, right? Minus half of the gradient of E squared for the E field, and del dot B times B plus B dot, I'm sorry, let me factor out B field out of both of those dot products. B dot del times B minus half of the gradient of the B squared scalar field. All right, so this is what we obtain if we take the divergence of the Maxwell stress tensor at any particular point in space. All right, so a lot of algebraic work that we've done, and I'd like to announce that this is all the algebraic work that we're going to do, because this thing is our equation 2, and if we're careful, all of this is exactly what we obtained as our annoying terms in the force density equation. This is exactly the divergence, the vector divergence of the Maxwell stress tensor that we've obtained below, right? So let me write below what the local force density was. The local force density that we obtained, I've symbolized that by small f, was divergence of E plus E dot del. Okay, I think we've actually omitted epsilon naught out of all of our calculations, right? It was an epsilon naught for the E field terms. We had an epsilon naught factor for everything, right? We had an epsilon naught factor for the Z terms, right? We have an epsilon naught factor here, right? We have an epsilon naught factor for the before the E fields, right? And this is actually a common mistake that people make. You know, they drop out the factor in when they're hurried and everything. And we've got the 1 over permeability factor for the B field, right? We've actually missed out the factors here. Anyway, okay, let me find some space. There's E naught, and let me also find some space for the 1 over permeability term. Okay, so the local force density that we obtained, okay, this is what we obtained. We obtained epsilon naught times del dot E plus E dot del times E minus half of the gradient of E squared scalar field plus 1 over mu naught times del dot B plus B dot del, right, times B. And note again that this is 0, but we're still writing that term in order to maintain symmetry between E and B, mathematical symmetry between E and B, minus half of the gradient of the scalar B squared field. Minus, we had another term, which was 1 over c squared times the time derivative of the Poynting vector. All right, so this gives you the complete picture of what's happening. So when you're saying that the local force density is all of that, you're basically saying that the local force density is the vector divergence of the Maxwell stress tensor minus 1 over c squared time derivative of the Poynting vector, of the local Poynting vector. And this, my friends, is the force law that you're looking at. Okay, this now seems like a lot because it is only two terms, and things are making a lot more sense. Now we're going to move on to the interpretation of what this represents. All right. All right, so the fact that the equation for the local force density can be written so simply invites an interpretation. So this invites an interpretation. Let's try to interpret what we just did. All right, so F is the mechanical force density felt by the particles. I'm using the subscript mechanical. Let's just abbreviate that by mech. This is felt by the particles in the field, right? So charged particles and charged densities and currents and current densities feel this force, right? That's what we evaluated, right? And that happens to be the divergence of the stress tensor minus 1 over c squared, the time derivative of the Poynting vector. So, okay, so what this means is that for a particular volume in space, let me draw the axes quickly. For a particular volume in space, right, we've got a certain volume. The rate at which momentum changes in that volume, right? In fact, it's momentum density that we're talking about. So I'll symbolize momentum density with the small p, and momentum, actual linear momentum, with big P. So the time derivative of the momentum density at this particular location, right, of the momentum density, so this is going to be the divergence of the stress tensor minus 1 over c squared, the time derivative of the Poynting vector. All right, so I'm gonna try to write this in terms of the big P now, right? So so then that means that the time derivative of the momentum, the total momentum, right? So I've written this in terms of the big P now, right? So if the momentum density is given by this expression, then obviously the total momentum stored is going to be given by the volume integral, right? Or even better, what we can do is we can say that the total momentum, the second order differential of the total momentum, relative to the first difference being the volume and the second difference being the time. So right, so this will give the momentum density, right, per unit time. So there's that dt. That's what that is, right? That's what that is. And in fact, this should actually be a fourth order difference, because this d tau dash is a third order term. D tau dash is dv cubed, meaning this differential volume element is a third order differential, right? But then we're not gonna look at the formalism too much. All we need is that the time derivative of the total momentum stored, and note that I've used a capital P here, right? The time derivative of the total momentum stored is going to be a volume integral of this thing, right? And that is by taking volume integral of both sides of this equation. So we're going to take the volume integral of the divergence of the stress tensor, right, minus 1 over c squared, and the volume integral of the time derivative of the Poynting vector everywhere in space. All right, so this gives the rate at which momentum stored, the mechanical momentum stored at a particular volume changes. So dp over dt, now this does not give the momentum density. This gives the total momentum that's stored in this differential volume, right? It's the total momentum that's stored. All right, and this actually is also the mechanical momentum, as I mentioned earlier. So, okay, so I'm going to bring this term to the left-hand side and try to formulate an interpretation of this. So the total time rate at which the mechanical momentum changes plus 1 over c squared times the total rate at which I can pull the time derivative out, yeah, since the time differences and the volume differences are independent. I can pull the time derivative out. The time derivative of the volume integral of the Poynting vector, right, out. All right, so this is what this second term becomes when it comes to the left hand side, and all of that becomes the volume integral of the divergence of the stress tensor. And I think you can see that we can actually apply the Gaussian divergence theorem to say that the volume integral of the divergence is just the surface integral, right? So we just integrate the tensor across the surface of the volume that we're integrating over, right, of the surface. So let me write this whole equation again. Now we're not considering arbitrary volume elements. Now we're considering a whole region of space, right? Now we're considering a whole region of space. There's a volume V, right? There's a volume V in space, right, bound by a surface S. And what we're saying is that the total time derivative of the mechanical momentum of all of the charges and currents, right? The time derivative of the mechanical momentum of all of the charges and currents plus the time derivative of this particular thing, the time derivative of 1 over c squared times the volume integral of the Poynting vector, the time derivative of this particular thing, we don't know what this is yet, right? So the time derivative of time rate of increase of mechanical momentum, that's the first term. You know, we literally derived the first term to be that, right? We derived the expression for the local force density, which was for mechanical particles, which was for charges and currents, right? And this is the term that we obtained for the second thing. Let this be something, right? So this is something that we found is equal to the surface integral of the Maxwell stress tensor over that surface, right? We're integrating over the volume. All right, so the interpretation is that, the interpretation of this is that this particular term is actually symbolizing the time rate at which mechanical momentum is increasing inside this volume. So it's the mechanical momentum of all of these particles, right? It's the mechanical momentum of all of these particles. So if this particle is going there, if this charge is going there, right? The momentum that's stored inside all of these charges and currents, the rate at which that mechanical momentum increases, this term provides. And this term we interpret to be the momentum stored in the fields, right? So because this interpretation is also justified by the fact that this term literally includes the surface, the volume integral over the entire volume that you're considering. You're considering the volume integral of a vector that involves E and B. So of course, this is a momentum-like term. This is a momentum-like term that you're volume integrating. This is a momentum density-like term, right? And you're considering the time derivative of that. So there is something else which increases, right, when you're providing something into that volume. So you interpret this as a momentum-like thing, you know, that's stored in the volume. So this is a momentum-like thing that's stored in the volume, right? Which, by the way, changes according to a certain time rate. So like, that's what we interpret this. This is the total momentum, actually the whole thing, right? Because we've got the time derivative as well. That whole thing is the time rate of momentum, time rate of increase, or it could be decrease as well, right? Increase of field momentum. That's what we interpret the second term as, right? Because the first term is a time derivative of momentum. The second term is a time derivative of something else. Let's interpret that as momentum itself, because it has the dimensions of momentum. You're integrating some vector quantity that's a resultant of E and B. You're integrating that over the whole volume, means that you're integrating some quantity which is a momentum-like quantity over the volume, right? Which means this quantity should probably give you that part of the momentum which is not stored in particles, which is not stored in the virtue of moving particles, but it is stored in the fields, in the very virtue of the existence of fields in that volume, right? So two things increase in the LHS, and the third thing is interpreted as the rate at which momentum is delivered to the volume V, right? So I think this makes perfect sense, because okay, this is like this is a form of the physical law that's analogous to the first law of thermodynamics, right? The first law of thermodynamics was that you give a certain heat energy to a system that goes to two places. That goes to a certain work that the gas does to an external system, plus that also goes to an internal energy change for the gas, right? That energy that you give to that system goes to two places. Either that system gets some of that energy out by performing a certain bit of work on another system, or that system increases its own internal energy, right? It goes in two places. So this equation is analogous to that, in the sense that you can interpret this as the dq that's given into the system. So it also makes sense because this is a certain surface integral. You're integrating a certain tensor through the surface, right? So it's like when you're integrating across the surface, over the surface, it's like you're seeing something that's coming inside, right? Only the surface terms matter for the Maxwell stress tensor, right? It's as if something's coming inside the surface. It's something's entering through the surface, right? So that's the Maxwell's stress. That's the Maxwell's stress tensor integrated over the surface, right? You're integrating over the surface. It's like something's coming inside, right? You're integrating over the surface. Once you've integrated over that surface, that gives the time rate of change of two things, right? Something that's coming inside the surface is contributing to two things inside the volume bound by the surface. It's contributing to, first, the time rate of change of the mechanical momentum of the charges and currents, and second, the time rate of a momentum-like quantity that seems to be stored in the fields. So that's what we call the field that's stored in the momentum that's stored in the field itself, right? So that's the interpretation of the whole momentum continuity equation, right? We call this the momentum continuity equation. The continuity of momentum equation, right? So in words, if we're going to put this in words, the time rate of change of mechanical momentum plus the time rate of change of the EM field momentum, the momentum that's stored in EM fields. So the time rate of change of the total momentum that's stored inside this volume, actually, right? The total momentum comes from two things. It's either the momentum of the charges and currents, right, of the particles, the mechanical momentum, or the other portion is the momentum that actually gets stored in the fields and does not go to the particles. So the two time derivatives, that is the total time derivative of the momentum inside this volume, that the time derivative of that is as if something's coming inside. That is, you take the surface integral of the Maxwell's stress tensor over the surface, right? Something's coming in through the surface, and everything that's bound by the surface is increasing due to this thing that's coming in, right? So that's the whole interpretation. And this we call the momentum continuity equation in electrodynamics. right? So one final thing that I'm going to write is that the momentum stored in the field, right, P of the field is going to be given by this particular thing, obviously, right, with that interpretation. And that, if I am to rewrite down here, is 1 over c squared times the volume integral of the pointing vector. Or another way to write this is mu naught times epsilon naught, permeability of free space times the permittivity of free space, times the volume integral of E cross B over mu naught over the volume that you're considering. So this is the momentum stored in the field. Or a more standard way to write this is momentum density stored in the fields. This comes without the volume integral, right? So you're taking the momentum stored per unit volume. This comes without the fields, considering momentum stored per unit volume. And that just becomes, all right, the permeability terms cancel out. That just becomes E naught times E cross B. Or if you want to write this in terms of the pointing vector, that becomes S over C squared. Or written even better, mu naught epsilon naught times S. So this gives you the momentum density that's stored in the field. And this is the continuity equation that's fundamental to understanding how momentum is stored in particles as well as the field, right? And how the total momentum of that's stored inside a volume V changes, right? The surface integral term is as if something's coming inside or going outside of the surface, right? All right, so we discussed about how we could reach to the force density equation written entirely in terms of E and B and the time derivative of the pointing vector, right? Once we discussed this, right, and by the way, we started from the Lorentz force law and we used Maxwell's equations to write the charge density and the volume current density in terms of the fields, right? We simplified using some product laws, and we found that the equation is actually symmetric for E and B. Once we reached there, we began on a totally different journey, introducing about Maxwell's stress tensor. We introduced what its general element was, right? What it meant to take a general element, right? What is a general element when I and J are the same, right? Y and Y, and what's it when I and J are different? That is T, Y, X. We discussed about what it means to take the dot product of any arbitrary vector with the Maxwell stress tensor. The dot product is in and of itself a vector and not a scalar, right? We discussed what it meant to take the divergence of the Maxwell stress tensor, right? And we saw how we evaluated one of the components of the divergence explicitly, right? And we saw how everything just magically fit to tell us that the divergence of the Maxwell stress tensor, when it is defined in this way, when its divergence taken in Cartesian coordinates yields exactly the 6 terms that were annoying to us in the force density equation. So we could replace this whole force density equations, the 6 terms in the force density equations, with the divergence, the vector divergence of the Maxwell stress tensor. And this gave us a very fundamental force law with just 2 equations and very simple to look at. And this equation with, some considerations about how force is the time derivative of momentum, and some considerations about, what's written per unit volume and how to, get from per unit volume to a certain finite volume, by volume integrating. With some of those considerations, all of these equations are redundant. They basically are all the same equation. We reached to this momentum continuity equation, which gives that the total momentum stored in the field the total momentum stored in the field, which is the mechanical momentum of all the charges and the currents, plus the field stored momentum, changes with a time rate that's given by the surface integral of the Maxwell's stress tensor over the surface which bounds the volume. So it's like something's coming in, and that thing that's coming in is going to two things. That's the mechanical momentum and the EM field momentum. We derived explicitly what the momentum density in EM fields is, and I think it's advisable to remember this result. That is permeability times the permittivity times the Poynting vector. Thank you. That was all.